Hi everyone, I'm Nazim Hassan and welcome to my Internet Engineering and Electromagnetics lecture series. And today's topic is related to inner cell analysis, and many of us are working on metamaterial, electromagnetic bandgap structure and reflectarray. So the knowledge will come very handy to this analysis of this inner cell. Now before diving deep into the inner cell approach, I'd like to talk about the Floquet analysis. And after finishing this section, you will be successfully able to interpret the mode of the Floquet waves, whether it's evanescent or propagating. So imagine we have a unit cell, and this is x, y, and z axis. The dimension of the unit cell along x-axis is A, and the y-axis is B. And there is a surface current which is flowing parallel to z equal to naught plane. That means xy plane. So we define the surface current J, and this is a vector, and we can decompose J into two components, X and Y, right? And Jx and Jy. Now let's say J is mathematically defined by this function. And this function is defined within the interval of X interval, and this is the Y interval. These are the dimension of the unit cell, all right, from here. So we can write down the X component of the surface current by this general equation xy n, and this is n equal to minus of infinity to positive infinity, and fx minus of na y minus of nb. N is the number of unit cell along x-axis, and n is the dimension. And similar, this is for the y-axis. Now, with the equation 1, we can associate a linear phase gradients. Phase gradients are periodic in nature. So we can include this phase information into this surface current equation, and that can be written as Jx xy n minus of infinity and n minus of infinity to positive infinity, and then the fx ma minus of y minus of nb, and the exponential phase term minus of j kx naught ma minus of j ky naught nb. And x naught and ky naught are the phase gradients along x and y axis, and they can be defined as k naught sine theta naught cos phi naught, and ky naught can be defined as k naught sine theta naught times sine phi naught. And the unit cell, they will form a beam in direction of theta naught and phi naught, considering these phase gradients distributed along the infinite array. All right. Now, if we take the Fourier transform of this equation 2, the surface current, then the Fourier transform of the surface current can be written as, let's say, this is J bar, the Fourier transform of the surface current, of the X component of the surface current, Kx, Ky is equal to 4 pi square divided by AB, and the Fourier transform of this mathematical function, f of x. Okay, so I will write it like this, Kx, Ky, and the continuation of this equation is n minus of pt positive infinity, and obviously there will be direct delta function, the Fourier transform of that exponential quantity. So it will be like kx minus of k x mn multiplied by direct delta function of ky minus of ky mn. Okay, and let's define equation number 3. Now, if we observe this equation, it's very, very clear that the spectral component, this is the frequency domain of the surface current. So, the spectral components of the surface current are basically defined at discrete points. Alright? And here, kxmn is nothing but the kx naught, the phase gradient along x-axis, plus an additional phase shift of 2m pi by a. And in the same manner, kymn can be written as the phase gradient along y-axis ky naught plus an additional phase term of 2m pi by b. So, if we transform back into the time domain, and this is the frequency domain, if we can transform back into the time domain, then the phase term will begin up here, the exponential term, right? Obviously, the inverse Fourier transform of this equation 3 can be written as gx xy time domain 4 pi squared by ab and kx ky bar, I'll define what is that, and then we have the phase terms minus of infinity to positive infinity and minus infinity to positive infinity, and then the exponential term jk xmn kx minus of jky mn y. So, sorry, this is x, not k, just y, time domain. So equation number 4, in the equation number 4, if we can further observe that each Floquet, actually, this is nothing but a plane wave, alright? Now these plane waves are basically weighted by a special quantity, which is known as Floquet mode. And the entire series is called the Floquet series. I'm telling again, these are basically corresponding to plane waves which are weighted by a special quantity, which is the Floquet mode. So Floquet mode indicates plane waves. And Floquet modes can be of two types. One is evanescent mode, and another is propagating Floquet mode. Now, this is very important. We have to understand what is propagating and what is evanescent and how to determine them. Because in the image cell environment, we assume that the image cell is surrounded by identical or periodic bounded conditions. So in order to find out whether the Floquet mode is evanescent or propagating, we have one equation. Here, we can define that kxmn is equal to kx naught times sine theta naught cos phi naught in cylindrical coordinate system. kxmn equal to ky naught times sine theta naught and sine phi naught, and kz mn can be defined as k. Oh, sorry, these are k naught and cos theta naught. All right. So, in order to find out whether the Floquet mode is propagating or not, we have to check this equation. Kx mn squared plus ky mn squared. If it is less than ky naught whole squared, if this equation is satisfied, then we call the Floquet mode is propagating. And if it is not satisfied, then the mode is evanescent. Okay? So you have to check this equation. Now, how to analyze the image cell? So this is the basic of the Floquet analysis. Now we know that what is the propagating Floquet mode in the image cell, and obviously we have to see what approaches are followed to analyze the image cell. So let's jump into that section. Okay, so let's imagine we have a rectangular waveguide. We have a rectangular waveguide, and inside the waveguide we placed our unit cell. So here somehow we placed our unit cell. This is z-axis, this is x-axis, this is y-axis. If we closely notice that the boundary of the waveguide imposes, actually the boundaries impose periodic condition on this structure. The walls of the waveguide are periodic in nature, right? They have periodic boundary condition. Now, we can define two ports at this end and at this end. We define two ports, that is Floquet port 1, FP1 and FP2. So from the port 1 and port 2, we inject the Floquet waves into the structure, into the immediate cell. And obviously, the wave will hit the structure, and there will be incident wave, and there will be some reflected waves, some scattered waves. So let's say the incident wave from the port 1 is a mm, and the reflected or the scattered wave of this port 1 is, say, cmn. And from the port 2, in the same manner, the incident wave is, say, bmn, and the scattered wave is dmn. Now, in every device in microwave engineering, they can be characterized by scattering matrix. So our next goal is to determine a scattering matrix that can define, that can contain all the information of the Floquet modes and angle of incidences, because the waves that are hitting this structure, the response will also depend on the angle of incidence. The angle with which they hit the structure, that will determine the response of the overall system. So we do need to consider the angle of incidence here. But normally, we consider the normal incidence. Anyway, so as I was saying, so we would like to determine a generalized scattering matrix, or in short we call GSM. We'd like to find out this generalized scattering matrix for this setup, which will include all the information of the Floquet incident waves and the scattered waves, and this will give us a complete overview of the system. So if you write down the scattering matrix equation for this system, we can say these are the reflected waves or the scattered waves or the scattered wave vectors. And there will be transverse electric and transverse magnetic modes associated with the incidence and the scattered wave. So there is the scattered waves are C in the port 1 and D in the port 2. So let's write C first for the port 1. This is the scattered wave. Scattered waves. So CMN for the transverse electric mode and CMN for the transverse magnetic mode, TM. In the same manner, for the port 2, the scattered wave was D. So DMN for transverse electric and DMN for transverse magnetic mode is equal to, we will have the GSM, or Generalized Scattering Matrix, I will write it later, it's a big one, and multiplied by the vectors which are incident waves, right? Now for the port 1, the incident wave was AMN, and for the port 2 incident wave was BMN. So we will write AMN, the first one is transverse electric, and AMN for the port 1, transverse magnetic, and similarly for the BMN for the port 2. The last one is transverse magnetic. So these are the incident waves, these are the scattered waves, and between them we have this generalized scattering matrix. I will write it now. S11, 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 S12, 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 S21, 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 S22, 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 S22. So for your convenience, I will just separate them like this. Okay. Now, as I was saying that there will be transverse electric and transverse magnetic modes associated with all incident and scattered waves. So we will write S11 first, transverse electric for both, and for here, transverse electric and transverse magnetic. And this diagonal component will be the opposite of this. So it will come transverse magnetic first, and then transverse electric, and the last one is for transverse magnetic for both. So in the same manner, if we fulfill, or if we fill up the superscripts, we can complete them very easily. It's very easy. Transverse magnetic, in the same manner, transverse electric, both, transverse electric, transverse magnetic, transverse magnetic, transverse electric, and the last one, transverse magnetic for the both. Transverse electric, transverse electric, transverse electric, transverse magnetic, transverse magnetic, transverse electric. The last one is transverse magnetic for both. So this is the generalized scattered matrix for which in which we have the whole information about the Floquet modes. Now let's consider these two port. This is a two-port setup, right? We have port 1 and port 2. But if we place a ground plane beneath this structure, then obviously we can eliminate the port 2 because from the below, if you see the reflection coefficient, there will be they can constrain these quantities. So this is port 2, and this is 2. Okay. So let's modify this picture a little bit. Let's say we have a ground plane right there. And here is the substrate. And on top of the substrate, we have this unit cell. And the height of the substrate, the thickness is h. And then we have the ground plane. Okay, zero potential. Anyway, so we have only port 1. For the port 1, we can eliminate this. And also we can eliminate this. And since we don't have the port 2, we can also eliminate this. Port 2, eliminate this. Port 2, eliminate this. So only existing is this. Now, I'm telling you, when you design the unit cell practically, we usually take the dimension of the unit cell either equal to or less than the half-wave length. Less than the half-wave length or equal to half-wave length. And if you consider this dimension, then only two modes can exist. Transverse electric 0, 0 and transverse magnetic 0, 0. Okay? So we can just write it or simplify this by one-port matrix. I will write it here. So the revised or simplified version can be written as CMN, CMN, transverse electric, transverse magnetic is equal to S11 transverse electric, S11 transverse electric, transverse magnetic, S11 transverse magnetic, transverse electric, transverse magnetic, and transverse magnetic, and multiplied by A transverse electric, Mn, and A transverse magnetic, Mn. Okay, so here we go. We have the simplified one-port matrix for this setup. And if we see the reflection coefficient curves from this solution, then obviously the reflection coefficient curves, we have the frequency versus S11. It will be depend on the different angles. So for different incident angles, the S11 will be also different. And we can easily find it by using any commercial electromagnetic solver. So I hope that this lecture was very helpful for the understanding of unit cell analysis and also the Floquet analysis. And there are other internet engineering tutorials in my channel. Make sure you check them. And thank you very much for watching.